Coming up on Dr. Kiki's Science Hour. Using an ice cube to probe the universe? We'll be learning all about neutrinos and Antarctica from Dr. Jim Madsen. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with Dr. Kiki and Leo Laporte. Episode number 28 for Friday, December 25th, 2009. Taking a cold look at neutrinos.
Dr. Kiki's Science Hour is brought to you by the new voice-activated Sync, featuring hands-free calling, music search, and turn-by-turn navigation. Available exclusively on Ford, Lincoln, and Mercury vehicles. For more details, visit syncmyridepodcast.com.
Welcome, everyone. This is Dr. Kiki's Science Hour, episode number 28. And today, we are talking with Jim Madsen about the Antarctic IceCube project. Now, what is the IceCube project? What's it doing in Antarctica?
I'll tell you, that's the best place for ice cubes, isn't it?
It is the best place for ice cubes. So we'll just get started right off the bat with the questions. Jim, you're a professor of physics at the University of Wisconsin in River Falls, and you've been working on the IceCube project for a while. More recently on the IceTop project. But can you give us a little background information about what this project is all about?
This is a project to look for what's out in the universe in a totally different way. So the analogy I like to use is that if we want to learn about new things in the universe, we have to use new techniques. And so we now have telescopes that will look at all different kinds of light, from real low energy long wavelength light that we call radio waves to very, very high energy light that we call gamma rays. But this type of telescope uses a different type of particle that will hopefully give us new information and then enable us to find new things. And so it's really what motivates me, and I think most of the people on the project, is the discovery experiment, where we say, because no one's ever made a telescope like this before, we'll be able to find new phenomena. And so that's really kind of what motivates this. And the good news is that these particles that we're looking for are the most common particles in the universe. The bad news is that they're very, very difficult to capture. So we need a huge detector. And that's why we're at the South Pole. We need basically 1 kilometer by 1 kilometer by 1 kilometer of clear material in order to make our detector. And so really the only way we can do that is we can either use ice or we can use water. And it turns out it's actually easier to work down at the South Pole than to work in the deep ocean for this experiment. So that's why we're down at the South Pole.
So are you actually using the Antarctic ice as the clear material for your detector? Is that the basis for it?
That's correct. It turns out, just kind of luckily for us, that the ice down at the South Pole is the clearest material that's ever been measured.
Wow.
So it turns out that we can't make ice anywhere near as clear and impure in the laboratory. And so all the measurements that had been done before, it suggested that the ice would be maybe 10 times less clear than it actually turned out to be. And that's what enabled us to use the ice down at the South Pole. So the light can actually travel for almost 200 meters in the clearest ice before it gets absorbed. And so it's the clearest, purest material that's ever been measured, actually.
Wow.
That seems so strange to me that in the laboratory you can't even produce as an ice as clear as what is down at the South Pole. Do you have any idea what the conditions might have been to actually allow for such clarity?
Well, the environment, the climate at the South Pole is actually quite undisturbed. And so there is actually a band around 2,000 meters deep where there was a global climatological event that deposited a lot of dust. And we can see that very clearly, ironically clearly. We see it because the ice isn't as clear, right? So the light doesn't travel near as far in that layer of ice. But in the other regions, the air that reaches the South Pole has gone over the whole continent. There's really no sources of any pollutants, right? So really the only way any dust gets in is if there's a big event that's putting dust from
like Krakatoa or something.
Right.
Yeah.
Exactly. Some real big, large event like that.
Yeah.
So.
Wow, that's neat.
All right. So you found the clearest material on the planet down at the South Pole, and also plenty of space. And you've built a telescope, or you call it a detector. I mean, when we think of a telescope normally, I think most people think of what you see in an observatory, where you have glass lenses and a long tube for the light and mirrors and that sort of thing. Is this similar at all, or is it completely different?
Well, so we actually call any object where you can get information about the direction, a telescope. So if you're going to look out in the universe and you can say, here's what direction that information came from, that kind of separates a detector from the telescope distinction. So there are some things that just say, we saw some energy, but they can't really tell you where it came from. Our device down in the ice actually will tell us which direction the particle came from. So it's called the neutrino telescope. So it not only tells us, what time we saw the neutrino, it tells us which direction and how much energy that neutrino had. And so the difference is that, and I think we get spoiled by the Hubble telescope. Whenever we say telescope, people expect to see these really brilliant images, right?
Yeah.
And we see, like, now with the IceCube detector, we'll see a few hundred neutrinos a day. So if we were trying to make a picture, it would be like trying to see what was on the cover of the New York Times by seeing a couple hundred dots a day. It takes a long, long time, and it really isn't all that impressive a picture if you're used to seeing like these really beautiful color photographs that come from a Hubble Space Telescope. Yeah. So even though it's the largest detector that's ever been built, the largest telescope that's ever been built anywhere, we still only see, as I say, about a few hundred of these neutrinos a day. So it takes a long time to collect enough information to learn what's out there.
Where are the neutrinos coming from?
Yeah.
So we're looking for very high energy neutrinos, and so they're going to be produced in what we call cataclysmic events. So things that are very, very violent. So if you rearrange electrons, that's a chemical reaction. That has a amount of energy on a relative scale we'll call 1. If we rearrange the protons inside the nucleus in an atom, that's like nuclear reactions that go on inside the sun. That produces about 1 million times more energy. Our telescope looks for particles that are 1 million times more energy than the nuclear reactions. And so they're going to be created like when maybe a black hole collides with another star, or in these very energetic events called gamma ray bursts, but things that are very massive and extremely high energy in order to produce these neutrinos that we're looking for.
Can you tell us, just define the neutrino? They're subatomic high energy particles. Is that pretty much what we need to know?
Yeah, exactly.
Well, I know from the science comic that they're just passing through.
They're just passing through.
Yeah, I know that much.
Passing through. That's the good news, is that they, for the most part, they go right through you and I. In fact, something like 100 trillion per second go through you and I. But in our lifetime, only about 1 will actually hit an atom inside our body. And so that about once every 100 years. So that's why we have to make this detector so big down at the South Pole, because we want to see them more often. It's really only been about 100 years since really even scientists agreed that atoms were real. And it's been less than like 70 years before we had this idea of what we call the, kind of this planetary model, that the atom, I think most people would be comfortable if you said the atom has electrons and protons. And I think,
right.
Again, if it had some chemistry, they'd say, and there's neutrons, right?
Right.
But it turns out then, if we keep smashing these atoms up, what we find out is the electrons don't seem to have any parts inside of them, but the protons had some parts inside. And go ahead.
So these atomic particles weren't completely atomic. They had subparticles.
Right. So the original idea was that, atoms were the smallest divisions, right? And then we found out that atoms were made of these subparts, the electron, the proton, and the neutron.
Right.
And then we found out that there's really almost literally hundreds of other particles besides electrons, protons, and neutrons. And so the neutrino, it turns out, is in the same family as the electron. It doesn't have any electric charge, and its mass is very, very small. We now know that it does have some mass. So in some ways, it's just another particle that's out there, But and I think that, in another, who knows, depending on how successful we are, in another 10, 20 years, the kids in high school will be talking about neutrinos just like they talk about electrons and protons and neutrons.
Yeah. So you mentioned that, it's been between 107 or 70 years basically since we've really had this idea of the atom as having these the atomic model, so to say. And then how long has it been that we've been talking about the neutrinos and other subatomic particles? Is that really just like 20 or 30 years or so?
Yeah, so what happened was about 1930, the original idea of a neutrino came along. It's kind of the analogy I like to use, although with electronic banking, this is probably going away, but it's like a checkbook where at the end of the month, you'd say, it doesn't balance, we'll just throw in $5 and then we'll call it even, right?
You've seen me do my banking, obviously.
Exactly. And so that's the way the neutrino was introduced. They had these radioactive decays, and they couldn't account for the energy. And they said, well, let's just say that there's another particle we call a neutrino that's carrying away some energy. But it had to be neutral, and it had to be very hard to detect because they couldn't find it.
Right.
And then it took another 25 years before somebody came up with an experiment that would detect the neutrino directly. And so so that's like the 1950s. It wasn't long after that before someone came up with the idea that you could maybe do astronomy using neutrinos. But they quickly realized you would need a detector that was 1 kilometer by 1 kilometer by 1 kilometer. And the way we detected neutrinos was very expensive. So that was billions and billions of dollars. And so until somebody thought of the idea of using ice, it was cost prohibitive. And so, that's kind of the idea there. But, part of the problem we have is science is really separate from the rest of society. And so things that are 30, 40 years old in science often take a long time to get into the everyday language. Yeah. And so particle physicists have been comfortable with this idea of neutrinos for 40 years. If you're not a particle physicist, you don't really talk about neutrinos, right? Because they're not so important unless you're doing that kind of work, right? So, but now, it's a very exciting area of science, and there's a lot of experiments going on because it actually connects both the work that's going on in Switzerland at this new Large Hadron Collider and the exploration of the universe. So it's kind of bridging, and so this there's this new area called astroparticle physics, right? And so, I think it will be, as I say, something that will come along where people will say, "Oh yeah, everybody knows about neutrinos."
Well, especially with these huge science projects like the Hadron Collider, like the IceCube project, as they get into the public consciousness, people are going to realize, oh, there are these particles. This what you say, astroparticle physics, will probably become a much more common term and a common endeavor for physicists.
Right, and I really think that this era will be as revolutionary as any other period in science. The what's going on right now with the understanding that the ordinary matter is at most a few percent of what the universe is made out of. So I think we always tend to look and say, oh, look at how simplistic people's views were, right? 100 years ago. I always make that joke when I'm teaching and say, I could have thought of that. Right? But,
right.
They get their name in the books, right? Yeah.
So you think 100 years from now, people will say, "Oh, that Niels Bohr, he was such a putz."
Yeah, exactly.
I could have thought of that.
Yeah, exactly. But people are going to look and they're going to say they didn't even know about this type of matter, right. And that's 25% of what the universe is. They don't know what this dark energy stuff was, and that's 70% of the universe. And they spent all their time talking about atoms, and that's just a few percent.
Yeah.
I love that because I think sometimes we feel like, oh, we know everything now.
Right, and people have written books. There was a book out a couple of years ago called The End of Science.
Right.
People, every few years, someone decides, oh, we're getting to the point where there's just not that much more to learn. There aren't going to be that many huge discoveries coming out. But I think that's completely wrong.
Yeah, and so, just like in medicine, right, in order to get new information, in order to make that progress, you have to come up with new technologies, right? And so one of the analogies I like to use is if you're trying to understand how the brain functions, right? Yep. You can take x-rays all day long, right? And unless somebody has a skull fracture, you don't discover anything new. But now with, either magnetic field imaging or with PET scans or things like that, now you can really start to look at functions, right, inside the brain. And that really revolutionizes maybe, the way we think about how the brain operates, right? And so it's the same analogy with this astrophysics business, right? Is bringing on new techniques enables you to get information that really opens up whole new areas of investigation. So
yeah. So with the neutrino, the IceCube neutrino detector, there are other neutrino detectors. Camland in Japan is a neutrino detector, right. Is it not? What are the fundamental differences between the giant mirrored water-filled detector versus your IceCube?
Yeah. So one way to think about it is like looking at a net for catching fish. So if you want to study little fish, you need a very fine net, right? And maybe not as big a one, because you only need to catch a certain number of fish. But if you want to catch a very large fish, then if you have a fine net, it's going to fill up with these little fish that you're not really interested in. So the detectors, like there's one in Canada, there's also the one in Japan that you mentioned. They were looking for neutrinos that were created from the sun. And those are, in round numbers, 100,000 times less energy than the neutrinos we're looking for. So our detector is big but sparse. And so the neutrinos that come from the sun go right through, and we don't measure those guys. Okay, they don't make a signal big enough for our detector to say I saw something.
Wow.
And so ours is much, much bigger, right? Probably 50,000 times bigger, right? But very open. And so the technical language is we say it doesn't turn on, it doesn't see something until the energy gets very, very high. And so because in some sense we've made a decision that the interesting things are coming for these higher energy particles. So that's the difference. So
I know what kind of phone you have.
all right. Sorry about that.
Funny.
Yeah. So it's opening up this new energy range. As I said, just like you can see different energy ranges of light, we're looking at these very high energy neutrinos in order to learn about hopefully new and exciting phenomena that we can't see with other techniques.
Yeah, so let's talk about the science a little bit. When you detect something, you said earlier you can the detector will tell you how much energy and from what direction the neutrino came. But what do you correlate that with, and what do you then do? Like what do you analyze and what do you try to learn?
Yeah, that's when I give these presentations at schools. Almost always, one of the kids will say, "What do you do with the neutrinos after you catch them?"
You put them in a cage.
Like we have them in a bottle, right? Yeah.
Like a jar of fireflies. That's my jar of neutrinos.
Right. Yeah. Here they are. There are a number of different types of investigations we do. So for example, one that's kind of relatively easy to understand is there are these very, very incredible explosions that happened once or twice a day somewhere in the universe called gamma ray bursts. And what happens is that once or twice a day somewhere in the universe there's this giant explosion, and it puts out more energy in gamma rays than the whole rest of the universe combined for sometimes less than a second, sometimes for a few tens of seconds, and then they just go away. So one of the questions we have is, are these gamma rays accompanied with neutrinos? So there are experiments that measure the gamma rays. We're looking to see, are there any neutrinos coming with that? So what we would do is we know from these other experiments which directions the gamma rays came from. So one of the things we look for is, do we see a neutrino from that direction at about the same time? And that would tell us something about what's producing these large bursts of gamma rays. So that's one example. Another example is we look and we say, are there neutrinos coming from the center of the sun that are high energy? And it turns out that would be, if certain other criteria are met, an example of these dark matter particles that get trapped in the center of the sun and then knock into each other and produce neutrinos. And so by looking at other characteristics, we can identify where they came from. One neutrino by itself looks like any other neutrino. So there has to be some other piece of evidence that connects it with some other phenomena. So that's kind of the thing where you need to have complementary experiments going on in order to know, or theories that say, if we see this many neutrinos from this direction, then it's being produced by this type of object.
Yeah.
But otherwise, it's like if we see some light come in, the only reason we know where it came from is we look up in the sky and we say, there's an object up there, right, in that same direction where this light's coming from. So then we say, yeah, that came from that star, right? So
I think it's just a fascinating idea that we can get an idea of what was happening, where things came from by these particles that are just passing through, that we can, get a little snapshot of them as they pass through, and get enough information to be able to correlate it with events, with things happening in our universe. That's really neat.
Yeah. And so what we do is we actually melt these holes in the ice and then put these extremely sensitive light sensors down. The ice down at the South Pole is 3,000 meters thick, so over 1.5 miles thick. And we melt holes that are 60 centimeters, so roughly about 2 feet in diameter, 2,450 meters down. And then every 17 meters, so roughly 50 feet, we put a light sensor.
Wow.
So altogether, we'll have about 80 plus another 6 or so of these holes that are spaced 125 meters apart, and they'll form a giant grid down in the ice of these light sensors. And then when the particles pass through, they give off light. And then by the timing, we can tell the path of the particle as it goes through the ice. So what we actually get is information of how much light is seen and what time it's seen at each one of these sensors. And then from that information, we can reconstruct the path of the particle going through the ice.
Right.
I hope that didn't get too complicated.
No, I thought that was perfect.
Well done.
It was great. I think it was very, very simplified for.
And I have some pictures. The website is www.icecube.wisc.edu, and there's lots of great stuff, including a lot of educational outreach. I mean, clearly you want students to know what you're up to here, not just college students or grad students either.
Right, and that's another aspect of what you're doing. There's been something recently. We tried to get on a high school teacher who's been down at the Detector, but he wasn't able to join us today.
Wow, you take high school teachers down. That's neat. Yeah. That's really great.
Yeah, can you talk a bit about the outreach that you do, Jim?
Yeah, so the IceCube project, has a major commitment to bringing this research beyond the research community. And, there's lots of exciting science going on, but what separates this project from other equally valuable and exciting stuff is this one's being done at the South Pole. So people will talk to you that won't talk to you normally, right? Because they want to hear about the South Pole, and then they'll listen to the other stuff as well, right? But, for example, if you look, the things that are going on in Switzerland, are equally groundbreaking, but it's not an exotic, locale. And so you don't get as much interest from the general public. So there's a very good National Science Foundation project called Polar Trek, which pairs high school teachers, or actually grade through middle school and high school teachers, with polar researchers. So we partnered with the Polar Trek program and with a private foundation, the Knowles Science Teaching Foundation, to leverage the resources of the IceCube project and the Knowles Science Teaching Foundation and Polar Trek to send this teacher from teacher from California, Casey O'Hara, down to the South Pole, and he was an actual member of the team. The population is really tight down at the South Pole, so we can't have people just sitting around for 3 weeks down at the South Pole. So he was down out in the field, getting tanks ready to get filled, hooking up detectors, doing all the work that I would have been doing. So it was nice for me because I've been down there a couple of times, so it's good to have somebody else do some of that work as well.
Yeah,
so,
I would imagine.
Yeah. So the Knowles Science Teaching Foundation is really a nice project as well. What they do is they identify exemplary professionals who are in the first few years of their careers who have decided they want to be teachers, and then they go and support them so that they can get their teaching certificate. And so there's roughly about 120 people who have either gotten their teaching certificate or in the process of doing that. And so Casey is one of the first teachers that was selected by that program, has been teaching physics for a few years in California. We have another teacher, Katie Sheary, who will go to the South Pole next season with the IceCube, who's also a member of the Knowles Science Teaching Foundation group. So
what a great opportunity for those teachers. I think that's just really fantastic.
I mean, and I'm just imagining what it must be like to go down there, have the experience, and then be able to take it back to the classroom with you, and it would just add so much to what you could give to students as a teacher, just from personal experience.
Yeah, I think that whole idea, as I said at the beginning, about that science is a live and vibrant area, and not just a big thick book that you have to learn.
Yeah.
And I think the other thing he brings back he'll bring back is just this idea that while we know lots of stuff, there's tremendous amounts that are unknown, and the difference between working a problem where you know the answer and then you check to see if it's right versus, in some sense, making it up as you go with some guidance, to say here's what we hope's going on. And so I think it's really phenomenal. And I think the other neat thing is that these teachers are all very young, so they aren't more than 10 years away from a high school senior. So it's not. I always joke and say, so you don't have to be an old man like me, right, to do science.
And they're still enthusiastic too.
Exactly.
They don't. Do they mind? I mean,
they don't mind the cold.
that's another thing. So working down at the South Pole.
Look at this.
It's seasonal, right? Is the detector only working seasonally? Do you only have a few opportunities a year to be able to access it? What's the experience like being down there?
So kind of the cutoff is about 45 below Fahrenheit. So if it's colder than 45 below, then the equipment doesn't function. And so roughly about the end of October is when the station opens up again at the South Pole, and the first flight will come in. And then we work till about the middle of February. And then the last plane leaves. We have 2 to 3 scientists every year that stay then for that 9 months, from the end of February till the beginning of October, or the end of October. And there's roughly between 35 and 50 people, depending on the year, that's called winter over down there. Mm-hmm. And so they're there, and nobody can get in or out. They're running the detector if something. One of the things we often have trouble with is it's very dry, and so we have difficulties with static electricity inside. And so occasionally, a bearing will go out on a power supply and they have to replace the power supply or something like that, right? So they just check and they do things like that for us. Then, as I say, so there's about typically in round numbers, 45 to 50 people that winter over. So right now, during the summer, will be a balmy, typically about 20 below, right? When you say that's good working weather, right?
No.
And so there'll be about, in round numbers, about 250 people down at the South Pole. About 50 of those are working just on the IceCube project.
Wow.
Directly on it. So it's the biggest project that's ever been single project that's ever been done in Antarctica, and roughly about a 9-year, 8 to 9 year construction cycle, because we can only work about 3 months out of the year, and we have to put everything away and then start over again. So, and we'll have one more season of construction, so we'll finish the detector next year.
So, and when it's completely up and running, I mean, it's already, are you already starting to collect data, or is it you're still waiting and next year will be it when it turns on?
No, we're actually collecting. We can, from the moment, the first string went in the ice, the first season we only got one hole drilled, it was starting to collect information. And so it just collects more complete information and more particles the bigger it gets.
Right.
And so so basically, in round numbers, when it was half completed in 2 years, it would see about as many particles when it's fully completed as it would see in 1 year. So but when it's fully completed, we can measure the energy of higher energy particles. Because what happens is, if the particle goes all the way through the detector, then all we can say, depending on the size of the detector, is it had at least this much energy. So if we see the particle start and stop in the detector, then we can say this is exactly how much energy it had. But if it goes all the way through, we don't know how much energy it had given up before it got in and how much it gave up after it left.
Right.
And so the bigger the detector, the more information we can collect about the particles that way.
Will the detector be able to make any confirmations about dark matter, or is it strictly just neutrinos?
Yeah, so it turns out that people are quite clever, and so it was understood early on that we could do this work with dark matter. As I say, it's a crazy thing, but this dark matter would be left over, and it has to have the property too that it interacts very little with ordinary matter. So it can actually get trapped inside the Earth and inside the sun. And so if it's a certain type of matter, then what's predicted is that we'll see neutrinos come, higher energy neutrinos than are produced in the sun, come from the sun. And so we have experiments that are set up to look for those neutrinos from coming from basically the sun. And so that would be an indication of dark matter.
Yeah. Is there any way you could tell the difference between a particle that came from the sun, specifically from the dark matter that's trapped in there, or one that was just traveling through from somewhere beyond the sun and that just passed right through the sun?
Yeah. That's what makes this business tricky, is because you don't see lots of things, right? And so, but it turns out the difference between 1 and 2 is huge, right? And so if you see 1, you say, well, it could have been a coincidence, right? If you see 2 and they have the right energy and, they're not connected with something else, you can imagine other circumstantial things that might explain it. If none of those other things are there, then you become more and more confident, that it's from dark matter. But there's actually quite detailed predictions on what you should see. And so while you can't ever definitively say, absolutely, this is it, you can say, there's only a 1 out of 10,000 or 1 out of 100,000 that this was something other than, a neutrino that was created from dark matter.
Right.
And so that's the kind of criteria we kind of look for, is that we say a 3 sigma or a 5 sigma detection that basically corresponds to what are the chances it could be just accidental.
Right. Okay.
And so it's kind of, like in medical fields when they say, did this exposure cause cancer? Well, you can't really say definitively, but if you, in any one case, but if you have multiple cases, then you start to build, the evidence that says, look, this many people were exposed, this many people develop this kind of cancer, they don't seem to have any other exposure. So we start to build the case that, that's what's causing that particular type of cancer. And it's the same type of thing.
Right.
Except that you have much smaller numbers. Yeah.
So you end up with a probability
approaching, zero or the opposite.
Yeah.
As close as you can get.
And as I say, the funny thing is that the difference between 1 and 2 makes that probability go from being, it could be coincidental, to being almost for sure that's what it was. Right? So the difference is, it's not, we need 1,000 or 100,000. It turns out in this business, 2 things from the same direction are, everyone cracks out the champagne.
Scientists are very comfortable with probability and likelihood, and I think the general public always wants certainty, and there's no certainty in science, right?
I think
very little certainty. Yeah.
And I think, like in your field as well, right? You make correlations and so forth, but on an individual event basis, to say exactly this is what's going on and this caused this is really a difficult case to make. Right?
Yeah, absolutely. Did we have anybody in the Twaken room at all, or is there
It's kind of quiet. I think we're so early in the morning on the Twaken that. But we have a couple. Let's go to Hippozoid.
Hippozoid
to start. Hi, Hippozoid. Welcome. You have a question for Dr. Madsen or Dr. Kiki?
Hi, Leo and Dr. Kiki. I had a question for Dr. Madsen. He had mentioned about their detecting between 100 and 200 neutrinos a day. It just seems like a dramatic increase, which he'd address, what this will lead to discoveries, if it'll ramp up the discoveries, or just expand on that, please.
Great question. Thank you. First of all, where are you calling from, and what's your name, Epizoid?
I'm in Seneca, South Carolina. I'm Hip in the chat room.
Great. Thank you, Hip. Good question.
Yeah. So that, as I say, I think the analogy of trying to figure out a picture from seeing just a few dots is the key, right? And so the more dots you see in that photograph, the easier it is to reach a conclusion as to what it's telling you. And so what makes this astronomy and not just a detector is that we'll actually be able to see enough that we can make a sky map. So instead of saying here's where points of light are coming from, we'll be able to say here's where high energy neutrinos are coming from. And so the neutrinos are the only particle that we know that can come from actually inside the object. The light and the other high energy particle that comes out actually comes from the surface of the stars. They don't tell you about the interstellar processes, what's going on inside. So by being able to collect enough of these, then you start to be able to do a number of different things. So, for example, one thing, kind of on the edge, but potential of future types of experiments is if you get a point source that what type of neutrinos it's producing, you can actually study the interior of the Earth, because if you know now what the neutrinos are like that are being produced at that source, then how they get changed as they travel through the Earth tells you something about what's inside the Earth. So besides learning about stuff out in the universe, we can actually learn more about terrestrial things as well. Does
that play into understanding more about the core of the Earth and how and the dynamics of the molten core that we have?
Right. So it would tell you something about the density, right, of the Earth's interior. So there's a number of potential applications of those sort that it opens up. But the real, as I say, for me, the real driving force is this idea of, being the first to look through a telescope, literally a funny type of telescope that you don't actually have an eyepiece, but and with the potential to discover something that we can't see using any other technique. So every time we've built a new technology of light telescope, we've seen things that we haven't been able to detect with existing technologies. So that's kind of to me, the most exciting thing is to say, we think that there's new and crazy stuff out there, and that we're going to develop this instrument that's going to be able to find that new and stuff that opens up whole new areas of science to investigate.
That's neat. We have some more questions, more callers, so we're going to take another question.
Devin Baines. Hi, Devin. Where are you calling from?
Hi there. It's Rocklaw from the chat room calling from Parliament Hill in Ottawa, Canada.
Yay, Rocklaw. What can we do for you? A question for Jim or Kiki?
I do. I wonder if you could contrast it with Canada's own Sudbury Neutrino Observatory, which is 2 miles down in solid rock in the Canadian Shield. I'd be curious to see what kind of information they're getting and the kind of science they're performing as opposed to Professor Madsen's project.
Yeah. So most of our work is looking at the objects that actually produce the neutrino. What the Sudbury Mine was interested in is actually the properties of the neutrinos themselves. And so there's kind of, two parts to these things. Once you know a neutrino exists, you can study the neutrino itself, or you can study the things that produce the neutrinos. And so we call the neutrino a messenger particle. It tells us something about, the objects that produce it. So the Sudbury Mine was primary focus was to answer this question about the neutrinos that were being produced in the sun. So they're so-called solar neutrinos. And the problem was there were some very detailed predictions, because we thought we really understood how energy was being produced in the sun. And it predicted the type of neutrinos. It turns out there's 3 different types of neutrinos that are produced. But when they did the measurements, they didn't measure the number that were predicted. So that either means we don't understand how the sun is producing energy, or something else was going on. And what they found out was, and the Sudbury Mine was instrumental in making this discovery, is these neutrinos are kind of diabolical, and they switch from one type to another as they travel.
I knew it.
The diabolical neutrinos.
And so they were being produced in the number we calculated in the sun, but when they got to the Earth, they had switched to a different type, and we weren't measuring that type in the other experiments. And so the Sudbury Mine experiment was designed specifically to measure all 3 types of neutrinos. And that showed that the total number was right, but they were just shifting from one type to another. So they're looking at relatively low energy neutrinos that are coming from the sun. And as I said, our detector doesn't see those neutrinos. They go right through and don't make a blip in our telescope. So we're looking for much, in round numbers, about 1 million times higher energy ones, so bigger explosions than the ordinary functioning of a star.
Your experiment doesn't involve any heavy water.
It does not. No.
Just
Ours
ice,
is
right?
just ordinary ice down there. Yes.
Thank you, Rocklaw. Great to hear from you.
Excellent. Thank you.
All right.
Thanks a lot. That was great.
We got more. You want more questions?
Another-
Mikey does work. What's your first name? Where are you calling from, Mikey? Are you there, Mike?
I don't really have any questions right now. I'm just kind of hanging out, Christmas shopping, and listening.
Oh, well, we're glad you're listening. That's great. Thomas Scriven, Scriven, do you have a question for Kiki or Dr. Madsen?
Hey, guys. I'm doing the same exact thing as Mikey.
All right.
Kind of
I'm glad you're listening. No, that's fine. We don't have any way of indicating that you have a question or not. So if I see your name in there, I'm gonna put you up. But that's fine. Yeah, that's great. It's good to know you're listening. Thanks for tuning in via Twaken. This is something new we're trying, and I think it's working quite well.
It is.
Yeah, you can listen via phone if you have a phone and
that's
dial that number, and the quality's quite good, I hear. So
fascinating.
Another way to use it.
Great.
Yeah.
Earl Wallace says Twaken is working great.
Yeah.
We're having. I'm really enjoying being able to have listeners' questions on. It's. I think it adds so much to the conversation and brings so much more to it. I'm fascinated, Dr. Madsen, in the idea that these neutrinos, they shift in their how much energy, their energy state, I guess. I mean, I'm just thinking about how we think of light and energy moving along the electromagnetic spectrum, and you can have an electron gain energy and be emitted, say, from an LED as a photon. So an electron can actually shift into what we call a photon. Now, does
it shift or just emit? Does it actually change into
it emits a photon, I guess.
It goes from one level to another level, and the difference in energy between those levels gets emitted as
a
visible
photon.
light.
So it's kind of the excess energy as it jumps levels.
Right.
Right.
So suddenly you have a photon that can shoot out. Now the neutrinos, do they similarly shift between these energy states like electrons? Is that what you're finding, just at much higher levels?
So what the neutrinos are involved when particles change identities. So in your body, for example, you have radioactive potassium, right? And that decays and out comes a neutrino. Okay, and so it depends on the type of radioactive decay, but what's happening inside the nucleus is either a neutron is changing into a proton, or vice versa. A proton changes into a neutron. So in that process, instead of the same particle going from one energy level to another, a particle is changing identities. The neutron changes to a proton and outshoots the neutrino.
Got it.
Or vice versa, right? And so it turns out when protons are going at high speed and they knock into something, then they will produce neutrinos. And that's the way we make neutrinos on Earth. There's a neat experiment at Fermilab in Chicago where they accelerate protons up to very high energies and then just slam them into cement or the ground.
Right.
And that produces a beam of neutrinos that then is measured up in northern Minnesota in the Sudbury Mine.
Yeah, so where they just recently found evidence of dark matter, possibly.
Exactly. Yes. Right next to the neutrino detector. Yeah.
Got it.
So, right. And so so whenever we have particles that change identities, neutrinos pop out. That's basically the role that they serve. And so it's not the same particle, but a switch from one type of particle to another, and then those neutrinos are involved in those.
Yeah, and we find there are neutrinos that probably not detected by the IceCube detector, but neutrinos from nuclear radiation. So from nuclear power plants here on the planet, because you have the emission, you have the change in radioactive decay of particles, that I would imagine that there are plenty of neutrinos that come from those sources and pass through the Earth as well.
Right, and actually, whenever you have a nuclear reaction, there's the capability of producing neutrinos as well. So that's the way the first direct evidence for the neutrino was obtained, was by putting a detector near a nuclear reaction, nuclear reactor that they could turn on and off, right? And so it was producing a large number of these neutrinos. And then to ensure that that's really what the source was, then they would shut off that reaction and say, yep, no, we don't see them. Because sometimes you can get fooled, right? You say, that's what I'm measuring. But if you have a way that you can then verify that when you turn off that source, the signal goes away. And that, of course, you can't do with the sun. That would be bad, right?
Yeah.
So
we want it to keep going, keep going.
Yeah. So, but with smaller reactors, nuclear reactors on the Earth, we can turn them on, turn them off, and verify that we saw neutrinos on the rate.
Right. So we could use them to figure out whether or not North Korea or Iran were producing had nuclear reactors online, right?
Yeah, that's sometimes there's all different types of motivation for doing things, right? And sometimes the motivations are security, and in fact, the way these gamma ray bursts were detected was just for the purpose that you mentioned. So when a nuclear bomb is set off, not only does it produce neutrinos, which are very hard to detect, but it produces gamma rays. And so the U.S. Launched these satellites in the late 60s to look for gamma rays, because they were as a way to verify that the Soviets weren't setting off nuclear explosions. And they saw once a day that there was a burst of gamma rays, and they quickly realized they couldn't be setting off that many nuclear bombs and that they had to be coming from outer space. But until that time, nobody had any idea, right?
Right.
So that was a case of where, security concerns actually led the science because of that technology. And in fact, if scientists had said, we want money to put satellites up, they would have said that was way too expensive, right? But for security, it turns out that wasn't too expensive.
Yeah.
But now that's
fascinating.
That's a common way of doing science, is to launch things on satellites. So.
Yeah, and hopefully there will be many more satellites launched and many more telescopes built in cold, distant places like Antarctica to help us get more information about our universe. We're about at the end of our hour, I think.
It's been really great. We don't have. We're out of Twakens.
We're out of Twakens. Great.
But thank you for those who called in, Rocklaw and Hip. It's great to get some questions from the audience every once in a while.
Yeah, and Dr. Jim Madsen, it's been fascinating speaking with you this hour, and I really appreciate your taking the time during your traveling period to join us and to talk about the IceCube Observatory and also about neutrinos and the science that's going on. If you're interested in more information on neutrinos or the IceCube project, you can visit www.iceCube.wisc.edu. And also, if you want more information on connecting teachers with polar research, you can go to PolarTrek, PolarTrec.com, and the Knowles Foundation, which is responsible for those teaching fellowships, www.kstf.org. So there's a bunch of resources out there for people who want to investigate this a bit further, and I'm sure that's just the tip of the iceberg.
You made a little joke. It's summertime right now. In fact, it's the summer solstice or winter solstice.
Please wait for others to join.
Thank you. Bye-bye. Right now in the Antarctica. So you must be on your way back down, Jim, at some point?
So
I scared him.
I'm not going down this season.
You're not?
Yeah.
Oh, no.
Yeah. So, yeah. As I say, we now have about 250 scientists and graduate students involved in the project. And so many of them, of course, would like the opportunity to get to the South Pole. So I've been there a couple of times, so I haven't pushed real hard to get back. So we have these teachers that are going, and then some of the
grad students
that have joined the project. Yes. Right. So it's an interesting thing about the goals. We want to build this detector, of course, as efficiently as possible, but we also have an educational component. So by involving the teachers, involving graduate students, we build, for that future capability, and hopefully excite people to, learn more about science and maybe get more students interested and involved. So, the more people get to go, I think the better.
The website is great. You've really reached out to the public with the website. It's well done. I mean, I think it's just fantastic. Really,
thank you.
Yeah, really great experience.
Well, thank you so much for joining us and on this eve before Christmas Eve during the holidays. Wish you a very happy holidays and a fruitful research season.
Thank you very much.
Thank you, Jim.
You're welcome. And I'm Dr. Kiki, and this has been Dr. Kiki's Science Hour. We will be back next week to talk about the atomic clock, and we will be talking about the atomic clock with someone from the National Institute of Standards and Technology.
Yeah, NIST.
Yes, NIST. On New Year's Eve.
Oh, that's perfect.
It was. This was a suggestion.
Do we have a jump?
Dane,
do we have a jump second this year?
A jump second? That's something we can ask. I'm not sure if we have.
I think we had it a couple of years ago, so I think we're all caught up.
Shift your clocks forward a second.
Yeah, I love that. Oh, that'll be fun. The atomic clock. What fun!
Yeah, I think it'll be a really neat conversation. And once again, if anybody has any questions or any comments about the science of time, I guess could be fun. We are using Vidly this week. We didn't use it. vid.ly is the website. You can go and record a video and then tweet your video with the hashtag #DKSH. And we'll look for it and try and get your questions on the air. It's another way that we want to get you involved with these science conversations and see what the researchers can tell us. What can we draw out of them, these scientist people?
We learn from you.
We learn from
These
you.
strange quarks and twisted particles.
That's right. And you can find me online at Twitter at DRKIKI, I'm also online at drkiki.tv. It's my blog / website, and it gives you places to go, such as my other podcast radio show, This Week in Science, and other things I've been involved in. So if you're interested in more sciencey stuff, that's what I do, and that's where you can find me. And I guess aside from that, I'll see you next week. So thanks for tuning in to the Science Hour.